All right, let's get started. Hello, everyone. Welcome to the MIT Mobility Forum, episode 146. This is organized by the MIT Mobility Initiative. I'm Jinhua Zhao, Professor of Cities and Transportation at MIT. I'm very excited to have Professor Alex Bain from UC Berkeley join us today to present a large-scale project, Mixed Autonomy Traffic at Scale. How can a small proportion of an automated vehicle improve overall traffic efficiency? I invited Professor Bain to talk about two things. One is academically, what is the platform? What's the algorithm where a cloud-based system can broadcast high-level speed plan to fleet vehicles? And also the lower level specific vehicle are able to use a deep RL-based algorithm to control the surrounding traffic. But also I invited Professor Bain to share with us a really large-scale implementation. Professor Bain lead a big team consists of 5 universities, NSF, DOE, transportation authorities, infrastructure provider to implement the first time at scale experimentation of more than 100 autonomous vehicles on the I-24 freeway. Before I formally introduce Professor Bain, I do want to emphasize the norm of this forum. That is, everyone contribute one idea. Everyone, I mean the audience. Please type into the chat directly one question or comments to Professor Bain's presentation there. Professor Alex Bain is a Liao Chao Professor of Engineering at UC Berkeley, jointly appointed between Department of Electrical Engineering and Computer Science and the Civil and Environmental Engineer. He was the Director of the Institute of Transportation Study and now is the Director of the Center for Information Technology in the Interest Society. He's also the Faculty Scientist at the Lawrence Berkeley National Laboratory. 3 years ago, he was appointed as the Associate Provost for Berkeley Space Center to develop a major research campus, a joint venture between Berkeley, NASA, and private sector innovators. Professor Bain's research focused on the optimization models, control of distributed parameter system, large-scale infrastructure system, like a highway system, air traffic control system, water distribution system, and automation of transportation, both at the ground and air. Without further ado, let me pass the forum to Professor Bain. Alex, please.
Thank you so much for the generous introduction, Jinhua. I'm really honored to be on this forum. This is my first time. And so thank you so much for the invitation, and thank you, MIT, for making this possible. Just a sanity check, do you see my slides when I present them?
Perfect.
Thank you. Great, thank you again. So today I'm going to talk about mixed autonomy at scale. And if I go back to the history of self-driving vehicles, all the way back to the mid-90s when Berkeley was doing the first generation on the I-15, I think what's striking is that through the different phases the industry went, there clearly was a split at some point where on one hand you have approaches like Waymo where we go directly to level 5 for very specific geography and use cases. And on the other hand, you have the kind of a more global approach with incremental increase of autonomy, typical Tesla style, where, slowly it rises from level 1 to 1.1, 1.2, maybe all the way one day to level 5. And in both cases, I think what's interesting is that the question is in the meantime, when we get to either full penetration or one or the other, what happens to the world where humans have to coexist with vehicles with some level of automation? And so Kathy Wu, who is now a professor at MIT and who really is the one who historically cornered the term, really posed the problem very well in around 2015, which is how can we manage systems where we have mixed autonomy in which this paradigm of partial or full automation coexists with human-driven vehicle. And so the question that really came at the time that came from Ruben Sokar, who was the Deputy Assistant Director of the Department of Energy under the Obama administration was, in the world of mixed autonomy, is there a way to steer the entire system to something which is more optimal rather than in some ways leaving the negative consequences of automation? And so what Kathy did during her PhD, and that really started a kind of a 2-phase project that led to this experiment we're running in 2022 is the notion of could we control loosely vehicles with some degree of automation at a time when V2X has not happened, and where at best we can rely on cell communication networks, which are okay, but still suffer bandwidth and latency issues. And so the paradigm that we worked on at the time that led to where we're today was really first to create a cloud-based architecture to support mixed autonomy in the hope that one day we would be able to implement it. So in the entire talk, the color code is a car with some level of automation is in red, a car that is somehow partially sensed by the automated car is in blue, whether it's LiDAR, whether it's any kind of sensor, and a car that is just there but is not sensed by anybody is depicted in white. And the notion of mixed autonomy is that it first started in the longitudinal world. It's like, forget about the lane changes, just in the longitudinal control, could one, with a small number of vehicles, at least increase the efficiency of a single lane by just adjusting relative speeds and accelerations. And so what we built over the years was this infrastructure that is really kind of, in some ways, a revival of the automated highway system architecture Gen 1, where there's a planning layer on the top that somehow computes optimal allocation at the system level to all the vehicle it can access. And then it passes commands to the lower level, which are the local controllers running on the cars. There could be multiple of them. You can see on the left Toyotas, on the right Nissans, that execute commands on the basis of the plan, but only with local information. And the idea is that because the communication between the two layers is very bad, that's just our cellular network, you have to somehow be able to rely to some level of local automation that helps with the general plan that is sent upstairs. So if I start at the vehicle level, the idea is that you want some level of autonomy that can take a high-level command and yet act things locally. And so this literally started in around 2017, 16, 17, when deep reinforcement learning was really reaching its first renewal peak. And it became clear that you could use micro-simulation tools to train policies in simulation and then use transfer learning to implement them. And so this first generation of students, Kathy Wu, Abudi Kraidi, who is now at Google, Eugene Vinitsky, who is a professor at NYU, and Fangyu Wu, who is a postdoc at Cornell, created what was the first historical integration of deep reinforcement learning libraries onto the cloud, which at the time was AWS, with micro-simulation tools. And Sumo was the open platform we used. And then IMSUN built for us the first cloud implementation of their software IMSUN, and we were the one running it. And so at the time, the idea was, can we blend these three components to see if we can devise policies for mixed autonomy traffic? And if you go back in the history of traffic modeling, it's quite amazing, because the first traffic models go back 1935. Then if you fast forward almost 2/3 of a century, the famous Sugiyama experiment demonstrated that if you just have no autonomy, essentially humans are extremely bad at regulating things like spring stability, which if you think is a very simple phenomena, but humans just don't have the natural abilities to do that. And almost 10 years later, a team with another student of my group, Dan Work, who had in the meantime become a faculty at Illinois and now at Vanderbilt, demonstrated that with one single vehicle, you could essentially shave the stop and go oscillations that you observed due to string instability. And so this experiment that they run in Arizona in 2017 was quite revolutionary at the time, because this was the first time that you could really see active control in mixed autonomy works. In their case, the savings were around 42%. And so for us, that was the starting point of saying, okay, so now we have the flow framework, which can build these policies in complex cases. Could we try it in the real field? And so the other interesting thing that Kathy did when she was working is that she was able to replicate what the 2017 experiment was in 2018 with a deep reinforcement learning algorithm. But the major difference is that the algorithm that runs in the system, which you will see activate now, it's turning on, which stabilizes the ring, for the first time, did not have a model of the system. So in other words, this is black box deep reinforcement learning, where the algorithm just gets a rewards and figures out the optimal policy without understanding physically, if you will, what the white cars are doing, which for us is the pivot point at which we figured, okay, so if this can be done, then things on the freeway where we really can't understand what's happened because the complexity is even higher, likely could be feasible with the deep reinforcement learning. So the other students in the group at the time started to figure out how to use transfer learning, for example, to see how you could take policies that you train on the ring and extrapolate them in other contexts, like the merge here. So the idea is you learn a policy on the ring in simulation, and then you transfer it in simulation, at least initially, to see if it works in merge systems. And what was amazing is that in the merge case, we were able at the time to show that in the case of a merge where you create waves by inserting cars, essentially the cars learn to slow down preemptively if they can see it's coming, and that's something they learn on the ring. And that was really interesting as a concept, because this is in a sense what we thought we would apply to the freeway. And so the student at the time, Eugene Vinitsky, now at NYU, and Abudi Kraide from Google, figured that, well, it would be interesting to understand the penetration at which this would work on a real freeway. At the time, this was picked by science. They were excited when they saw the results. And what they were able to show in simulation is that maybe with 10% this would work, which is a very high number, which we could never achieve in practice. We didn't have enough vehicles, but at least give us a sense that probably this could be done. And so that was the motivation to see if we could build that architecture and deploy it in the real world. And of course, when you do deploy deep reinforcement learning algorithms in the real world, you have to be really careful, because it's very difficult to prove anything on them. And so another student who is finishing his PhD literally in 3 months now, came up with a way to embed the deep reinforcement learning algorithm with a typical reward function you would expect, like you see here in the reward box, with a safety filter, which we built on top of it, which then itself is embedded in the safety filter of the car. And so you could view this as the low level, if you will, of that mixed autonomy system. Everything happens in the car, and some information is fed to that algorithm, in particular target speed, and that comes from the higher level, which is what we call the speed planner. So we tried this first with 4 autonomous vehicles and 6 sensing vehicles. And what we were able to show at the time in Nashville on the I-24 is that this provides interesting savings in energy. And we were able to demonstrate that if you just do 4 cars on a single lane and kind of block the other lanes, in the case, we had like 2 waves in that experiment, so about 10 kilometers, and we encountered 2 waves. By essentially applying the algorithm without any global information, just local information, we were able to save 16% of energy on the vehicle itself. And then we saw that the vehicles behind it that were not running the algorithm, because they were just essentially driven by humans, also saved a lot of energy. So we were on 14% for the next one, 12 for the next one, and so on, which makes sense, right? Because if you're behind a vehicle that is actually smoothing traffic, whether you like it or not, you have to smooth traffic, or you have to at least adhere to what they're doing, because you can't pass the vehicle. And so that experiment, which happened in 2021, for us was essentially the green light to try a full-scale experiment, which is what we did the next year. And so in the next year, when we built the full architecture, we had essentially tested the local architecture, this little box here, the previous year. We figured, okay, so now what we're going to try to do is to use commercially available data that we can get live, because we couldn't produce our own traffic estimates. We don't have enough infrastructure, so we had to buy it, and see if we can essentially distribute a target speed plan to all the vehicles that would then embed it in their deep reinforcement learning controller in the form of a target speed, to see if now we can have this mixed autonomy coordination, where the coordination is really top down, because again, you don't have V2V or V2X. Maybe it's there, but it's just, we don't have it at scale. So the only coordination you can really do is a speed plan, where the top down thing is essentially fed to the vehicles. So for those of you who have dealt with INRIX data, it's data which has a certain level of quality. This is what it looks like. So if you've seen time-space diagram, essentially, it's good enough that if there's a bottleneck, you'll see it. If there's shock waves, you'll see it. It's 500 meters tessellation at a 1 minute speed. And a very simple machine vision algorithm will enable you to split and detect the bottleneck and separate it from the wave, so you know exactly what you're doing, because you can't change bottlenecks. If there's a car crash, we can change it, but you can smooth the waves that result from it, and that's what the algorithm is taken as an input. And so essentially, that data that is of a certain level of quality gets feed into some other high-level algorithms, which we have a suite of them. I won't have time to present them today, that essentially propose a target speed to all the vehicles that then have the liberty to take them or not, depending on the local traffic conditions. And this is actually, you were mentioning Jay, she's currently in Boston today at Harvard and maybe even at MIT. And so this is one of the algorithms that she came up with, and we call this the speed planner. So essentially, what you want to avoid is the speed predictions you get from INRIX, which show you that down the road, you're going to have these bad oscillations, which is really what you don't want to have for energy efficiency. And then it produces some form of blue curve, which you see here, which is what you should really do. Jay, hi Jay, she's back in Berkeley. So that's what would be more optimal. And because of social speed limits, in the sense that you really should not be driving at 10 miles an hour if traffic is going fast, too quickly around you, even though you're getting into a bottleneck, you have to do some clipping function. And so this is an example of what that concept I just showed on real data. So you can see the INRIX data is pretty noisy, but you can see that the corresponding speed plan that is generated from the INRIX data is much smoother. And that's essentially what the upper level ships to the lower level. And then the lower level can treat this as a target speed. And again, if there's local things that prevent it from being done, of course, they don't do it, but otherwise, that's the way the traffic is smooth. And so that's what's happening in this box here. And that gets shipped to a bunch of different controllers because different vehicles have different architectures. And so they will take these speed targets in different ways. There is an additional issue is that in practice, as we were discussing, maybe as a prelude to this conversation today with Jinhua, architectures are getting closed these days. So in some ways, it's not obvious that you would have access to your own intervehicular speed and heading anymore. Even though the car can see it, doesn't mean you can access it unless you really are at the core of the vehicle. And so in some ways, you have to do some form of inversion where you turn on the autopilot or the ACC of the car, and based on what it's doing, before you override it, you can infer what it's seeing if you can see what it's seeing directly. So a little bit of a subtlety here, but it's important because I think this is really where the architectures of the cars are going. And so with that, then you can essentially have target speeds that you give to the car and then enable them to take that information, put it in their ACC, which you overwrite, and then they start to collaborate with each other, where the collaboration is really by the speed plans they get. So again, when we implemented that at scale, which is the last thing I want to show today, we really did this in single lanes. So even though we were having vehicles in 3 or 4 of the different lanes of the I-24, each vehicle stayed in the lane and only smoothed that lane, and we did not do vehicle lane changes to do more control because that's a lot more difficult. In practice, what it does, and just so you have an intuition about what it does, is there is a vehicle in front of you, which is usually behaving pretty erratically. So here in that upper curve, you can see the speed history of the vehicle in front of you. You can't control. There's someone in front of you, they're driving the way they're driving, and of course they're accelerating and slowing down and accelerating, and you can see this in the orange curve. And you're behind it, and essentially your algorithm, which has taken over the longitudinal control of your car, kind of does the same with a delay. You can see the blue curve is slightly behind the orange curve. That's because it's behind it, and it's also lagging in time. And what it does, if I try to explain this on TV, would be, well, it does what the person does in the front, except it does it less extremely. So you can see the accelerations are less pronounced, the decelerations are less pronounced, and that's really that's the best of what you can do, given that, this is a freeway, you have to, in some ways, behave according to social norms. So we tried this on the I-24, which is an amazing test bed that was built by John Sprinkle and Dan Work, 2 of my amazing colleagues of Nashville in Vanderbilt. And so this is the best instrumented freeway in the world. I can say, if there are civil engineers in the audience, this is what it looked like when it was built. Dan Work took over the management of the entire architecture of the project and how they would build. And essentially what they did is they built these gigantic video camera poles, which you see the first one ever being erected. And now there is one every 500 meters on that freeway, which is able to produce an insane amount of data. You should all go to the I-24 Motion website. And so we were the first experiment to run on that test bed right after it was built, and literally a week after it was turned on. Now, to run the experiment, we essentially, we want to try this with 100 vehicles now, the whole architecture I showed. So we essentially established a field headquarters in a factory that had been kind of vacated by the previous occupants, and essentially set up a stage there and started mounting 100 radios, 100 of everything that would go in the vehicles a couple of months prior to the experiment. At the end, I'll show there's a lot of partners, but it's a multi-university project. Obviously, we all flew in our students. Then we got the 100 vehicles from the Nissan factory that was there. And so to ship, like every day we would have different algorithms we would run in the vehicles. So we installed our own internet system so we could ship at a time the algorithms one by one directly to the vehicles, because otherwise it takes a lot of time to update every day the algorithm. And then essentially some of the students who really knew vehicle hardware well helped us to unplug a bunch of cables in each of the vehicles and literally plug our hardware in the middle, replug them, power them with a battery, and install all the automation stack on all the vehicles. So for example, this is a Gracie Gum from Vanderbilt who explains how to bypass the power system so we can power our electronics. And then what you see in here is a bunch of cables where all the automation commands of the ACC goes, which is what you have to unplug to essentially be able to add some hardware that will enable us to run our algorithms. And the hardware was not really pretty, but it's a Raspberry Pi that runs local controllers that we can ship. And essentially, the way we would do it is we would have some board inside the factory, and it's like almost like an airport. You can see if the algorithm has been shipped, it's been recompiled on the car, if it's running on the car, and then you know it's ready to go. Then we recruited a bunch of drivers, which was another thing, because at the end of the day, humans were still driving the vehicles. They released the longitudinal speed control to the algorithm, but they still were responsible for lane maintenance. So we had to go everywhere from the bus terminal to the airport to the cafeterias of the universities to get 150 drivers, which is what it takes to have 100 people running kind of on an ongoing basis, which was quite an exercise of recruitment in itself. So then the drivers would come to the factory around 4 a.m. And then they would be split in two teams, the orange team and the yellow team. You can see the vests. And then Dan Work and John Sprinkle would brief them on what they have to do. And what they have to do was actually pretty simple. I'll get into it in a minute. And then people would be assigned to teams, and then we would rotate them just like you run an airline and aircraft, and you just put pilots in planes, and we would do this with drivers in cars. We had to kind of run a little bit of an army here because it was like 200 people managed in that factory. So it had a bit of an Ocean 11 type gig for a while. But at the end, what we gave the participants is very simple. We told them, okay, well, there's one type of car you'll be driving today. It's a Nissan. You see the little onion button here. All you have to do is to press it. Imagine you were doing your adaptive cruise control or your cruise control. It's exactly the same, but just know that instead of running the Nissan vanilla flavor cruise controller, it will be running our algorithm. So if anything unsafe happens or you're not comfortable, turn it off by either clicking on it or braking, and it will automatically disengage it. And if you want to re-engage it later, just do it by pressing the button again. Then they downloaded basically a Google Map feed where by scanning a QR code, they had waypoints, and they essentially were driving back and forth and back and forth and back and forth for hours. And when they needed a break, bring the car back in, put another driver in the car, and continue doing that. And essentially, as they were driving back and forth, they would be smoothing traffic. So while they were doing this, we were monitoring the entire operation from our headquarters. And essentially on the experiment, we had collectively, cumulatively over the duration of the experiment, 100 Nissan Rogue vehicles, 5 Toyota RAV4s, and 1 Cadillac XT5, which is great because essentially we implemented our algorithms on 3 different architectures, which is really nice because it gives us a sense of how that can scale across ISM brands. We run this airport style for a full week. And essentially briefed the drivers one by one before they left off. Here's the picture of Jay in one of the vehicles, and then if you kind of look at a day of operation, this is roughly what it looks like. So essentially, during the experiment, what you do is you just keep flushing all the vehicles. They run for hours and hours and hours, and we even had our own fuel truck to refuel them when needed. And then at the end of the day, when they're finished running, we put them back in the parking lot. So that lasted for about a week. At the end, I can show you amazing videos because it's freeway traffic. So freeway traffic is boring to watch, but okay, this is the freeway. And so we also ran a media operation at the same time. Some of the students gave a lot of TV interviews. It was really nice. And at our headquarters, we used the amazing infrastructure that Dan Work's team built, the I-24 Motion. I really encourage if you visit Vanderbilt to see it. That gave us a full view of what was happening. So just to give you a sense of the magnitude of the data, I mean, this is what the I-24 Motion looks like. It's phenomenal. This is the best instrumented freeway in the world. We were very privileged to be the first experiment to run on it, but if you have experiments, go to Nashville. It's really worth it. That thing can monitor anything you want to try on the freeway, and it's quite a spectacular infrastructure. To give you a sense of the granularity of the data it collects, this is a zoomed-in version of the data. I'll zoom out in a minute. So if you've seen space diagrams, each of the trajectory is a vehicle. If you see them crossing each other, that's because there's multiple lanes. We unbundle that later. And the speed encodes is encoded by the color. So you can see when it's red, it's not moving. When it's green, it's going really fast. And then the white trajectories are the trajectories of the automated vehicles, which if I zoom out, you get a sense of the penetration in that entire freeway. So you can see this is roughly what 1% of the vehicles look like at scale. This is what mixed autonomy is at a very, very low penetration. In some ways, that's the beginning. And there's places here with so many Teslas already that these numbers were probably trumped. But the point is that we're very far from 100%. But even with a few percent, you can do a lot. And the interesting part here is, of course, what we were trying to do is to shave the oscillations, which we did partially. But of course, this is a very low actuation system because we have a few vehicles. So my last result slide will be to show you how you can measure how well you've done with this kind of work. Also want to give a tribute to Alex Cabardones, who sent me the very, very, very first time-space diagrams in the history of time-space diagrams. You see this is on paper. So it's amazing how in over half a century, we have gone from a maybe 15 by 15 matrix into something which has millions of points. And it's a hi to Alex since he's just completed his 40 years of service here at Berkeley. This data is quite complex. And so maybe the last thing I want to show on the result side is how you measure the savings you have achieved. And so once you have split the traffic by lane and it looks much cleaner, what you do essentially is you look at things like this. So this is in some ways a variance plot of velocity acceleration pairs without the control. And you can see what happens there, right? Because you have low velocity, that's when people are stuck, and then positive or negative acceleration if they accelerate or brake, and then high velocity clusters. And so when you run the algorithm, what you see is that the two are bundled together more. I mean, there's still a stop and go pattern because with 1%, you can't control everybody. So you can only control local people. But if you compute the variance and the convex hull of the 90th percentile of the points, you see that you have drastically reduced the variation, at least locally. And that's kind of what you're trying to achieve with this form of mixed autonomy. Other things you can do is you can do folding plots where you essentially average with respect to a random self-driving vehicle, the field in front of it and the field in the back of it. And what you will find is that in general, the direct speed in front of an AV is in general worse than in the back. And if you compute the level of energy consumption in the back, you will see that statistically it's lower behind an AV, which is what you want to achieve with this. And then maybe, so this is another way to display the same data. And then maybe lastly is if you look at the speed distributions in the front of an AV as opposed as behind of an AV, what you see is that ahead of the AV, you have this pocket or this peak of low speed vehicles, which somehow gets shaved behind the AV. And it's saying that if you look on average, say 20 meters ahead of an AV, there is statistically a lot more people who are stopped than 20 meters behind of an AV, which makes sense because the AV would have gone slower and people are trailing it at a speed which is statistically higher. So obviously it's very unclean data. It's also data which is operated at very low penetrations. So maybe one day if we're able to plug the algorithms inside an existing brand rather than having the hardware ourselves, we could operate at a much higher penetration. But these preliminary results are very convincing because we can see that locally we achieve up to 10% savings in fuel. So that's awesome because that's what we wanted to do. And of course, there is hope that if we do this at higher penetration, then the efficiency would be improved even more. I really want to acknowledge in closing that this is a huge team's effort. It's not just me. There is 5 other faculty on the team. Dan Work, John Sprinkle from Vanderbilt, Benny Siebold from Temple, Benedetto Piccoli from Rutgers, Maria Rona de la Monache from Berkeley, and Johnny Lee from Uber, who joined us now at Berkeley. I want to really thank the 3 automakers that gave their cars for this, especially Nissan, who gave us 100 vehicles, but also GM and Toyota, and all the agencies who really believed in it, in particular the US Department of Energy and the NSF, because I think it was a big, bold bet that we did. But I think believing in us and believing that we could make it work was really helpful for the team to do this. And all the other industry partners, AWS, C3AI, DTI, and companies that helped us with this. So again, not a single group's effort, but really a big group effort with a lot of faculty. And kudos to the whole team for the help. And so I think with this, I'm going to open it up to questions. Jinhua, should I unshare the slide? Okay, perfect.
Yeah.
Thank you.
Thank you, Alex. This is amazing. There's a very high density of information in the 20 minutes we just had. Thank you so much. So I will start with a few questions, and then or we invite all the audience to put your question and comment into the audience here, right? So I will move from a little bit more technical discussion to the implementation, then the future prospect there. So start with the simple one. You said there's about 10% energy reduction here. How about the impact on congestion, the speed, any like a high level figure on this?
Okay, no, thank you. This is a great question and to have as a number one question, because the one thing I have not told is that we worked with fixed demands, and our goal is not to change throughputs or average speed. And that's very important because first for a philosophical reason, and second for an operational reason. For philosophical reason, we know that 1% vehicle behaving differently will not change congestion, in the sense that it will not change the imbalance between demand and capacity. That's not what we're trying to do. So that's why that's very important. And second, because of maybe more operational concerns, is that there's this thing called induced demand. So if we change speed on the average, then we have no idea what's going to happen next, because that's not something that's part of our model. So when we devised the algorithms in the speed plan that Jefu put together, one thing we're very careful is that we take into account the exit speed of the freeway at the last point we control, because that's where the throughput is controlled. And we make sure that the overall travel time is not changed, because if we do, then we're changing essentially the capacity. So we work at constant capacity, if you will, and constant travel time. But what we change is that once people are in the system, then they behave differently. So instead of fast, slow, fast, slow, fast, slow, they would go more smoothly, which doesn't change the throughput, but decreases the energy footprint of the traffic. And thank you for asking that question first, because of course the natural question we get mostly from the media is, oh, are you going to remove traffic jams? And that's absolutely not the intent here.
I see. Yeah, in a way, that's actually more a fairer comparison in terms of energy reduction here, right? Given that control. Thanks. Yeah. The second question is, you mentioned that there's a transition from this model-based control to the RL model free-based control. And then later now we've been talking about the physics-informed machine learning as a new trend there, right? Can you share with us your observation about this evolution of the different models, and which part of the physics or what we learned from the transportation theory can be injected into these machine learning-based models?
Okay, wow, this is another really great question. Thank you so much, Jinhua. So it's funny, I came from the partial differential equation world, so physics-informed controllers, which I've done for the first part of my career. And then in 2015 is when deep reinforcement learning had a rebirth, and we realized, oh, now these algorithms are able to bypass all these models, and we can beat it with essentially no physics-informed. So it's like going from one extreme to the other in a couple of years. And of course, with the limitations we know, because you got a deep reinforcement learning policy, you really don't know what it's doing unless you can explain it. And that's the whole explainable AI rebirth that happened maybe a few years after the deep reinforcement learning rebirth. So initially for a few years and up to the test you saw here, we did not really care too much about the explainability of the algorithms. But what's amazing today is that in the last 2 years with the rebirth of LLMs, okay, so now it's like another mini revolution within AI, we are now able to train LLMs to explain the algorithms that we built in 2017, 2018, and 2019, at the time kind of like black boxes. And so in some ways it's kind of closing the circle, because maybe we're not that far from being able to interpret the outcome of these policies in terms of the physics models we had before, also with LLMs, which is something we have not done yet. So the short answer is that in some ways, in the last 10 years or 8 years, we kind of forgot all we had done before with physics models, kind of happily living in the deep reinforcement learning world. But now we're coming back to it, because I think the LLMs gives us a chance to kind of tie the two worlds together. And in a few months, we'll be able to show things which you've seen all over the media now, where our LLMs can explain to us with our own words in English language what we're doing. Like literally, I could play you a movie later saying, hey, I'm the controller and I'm now speeding because I see that the variance of the speed 2 miles ahead of me is this, and therefore I do that, which is something we did not have when, of course, we ran the experiment.
Right, that's exciting trend. Another question is on the communication side, right? You mentioned that between the global level control, the micro level control, the communication is not perfect. Oftentimes we lost signal, etc. And also, I just learned that for the Nissan vehicle, even though the car sense was the preceding car's speed position, but you guys as a researcher do not have access to it, right? Yeah. How much of those things that I heard the performance, and if we how critical we should improve all this communication system and also open the some degree that the architecture of the car control system there.
Yeah. So okay. So it's a very loaded question. So I'll try to unpack it in at least one or two or three different dimensions. So first of all, we got absolutely terrified 3 months or 4 months before the test because we had worked with some cars. I'm not going to name brands. We have 3 brands. You will guess which ones. But we had essentially a 2021 car, and then we had a 2022 car of the same model. And the 2022 car had essentially locked the architecture in the 21 car. So in the 21 car, you could open it, you could access your velocity, acceleration, intervehicular distance, and things. In the 2022 car, you could not access it anymore. Of course, the car still has it, but we didn't have it. So that part was very stressful because that means that 3 or 4 months before the test, we had to add a super layer of inference on the adaptive cruise controller. So essentially you model the adaptive cruise controller, which you don't have a model for, but you model it. And based on what it's doing, you guess what it's seeing. And that's so gives you an estimate of these parameters you cannot sense. And that's what you use to feed your algorithm. That did degrade our performance a bit because obviously it's better to have the full sensing. We never quantified how much it degraded it, but for us, I think the most important part was to be able to just have a safe algorithm that at least could infer safely the intervehicular distance, even though we did not access it. On the but on the upper level part, and that's really Jefu's algorithm, is where we really got the most gains because if through the upper layer you can quote see 2 miles ahead of you. Because you have a measurement, then you can feed that as your target speed. That goes back to the argument of knowing the speed at the end of the freeway. And that's where you can really get the energy gains because you can brake anticipatively, which shifts the oscillations and essentially enables you to not have to reaccelerate afterwards. So the energy gains are really achieved at the upper layer, mostly because of the planning, and at the lower layer because of the smoothing and the less erratic behavior in some ways that the algorithms enforce.
Great, thank you. That also shows the high degree of resilience your team were able to deal with this kind of sudden shock. And
a lot of gray hair here since that time.
Thanks, Alex. Another question, moving more towards the implementation side, right? So what does it take to move this from a pilot to just a routine operation across the board, right? Do we expect, for example, would Waymo take some of the algorithm you developed to implement it, or Tesla, or some of like Central as an infrastructure provider, or does the state DOT some sort of impose certain constraint? What do you see this evolving into the future?
Yeah, no, great question also. I think 5 years ago, some manufacturer, again, won't tell names, already had the option to push next generation autopilot, just like, okay, on your app store, you get an update, or your laptop has a software upgrade. So the same has been true for some automakers as on 5 or 6 years ago already. And in some ways, if you have vehicles yourself with a certain level of automation, again, not giving any specific brands, every once in a while you click yes, or you won't even click yes, you won't know it, but essentially the thing has been upgraded. So what that simply tells is that many automakers today have an architecture that supports shipping a new algorithm directly. And what that tells us is that all we need to do is literally give them the source code and then shipping it. Now, we understand it's much more complicated because you have to certify it, you have to test it and whatnot. But architecturally speaking, I think 5 or 10 years from now, almost every automaker will be able to just take this and push it. So that raises the second question is like, what's the incentive and the economics of why? So there is definitely, and this is all the Nash equilibrium thing, because if one does it, you lose, but if everybody does it, everybody wins. There is definitely an incentive for an automaker to have something like this, because you do save gas for yourself. So if some of your customers are interested to have their vehicles drive in a non-intuitive way, it's in some ways going slower when there's still space for you to go faster in front of you, because the algorithm knows that ultimately that will save money because you don't have to brake too much and then reaccelerate too much. Then there is an incentive. It's socially changing the norm. So there is for sure, market adoption thing here. But I think the real opportunity is regulation. I mean, so if you think of places like Singapore with the ERP program in the context of dynamic tolling, this is an example of a public agency that can change regulation, in that case, in the case of pricing. So if there is a regulation of public agencies, and this is really a call of action to, if there's people here who work in the audience who work on regulations, it really is something to think about now. A public agency could regulate and say, you know, if you're running some form of adaptive cruise control above a certain level, say level 1 or 2 or 2 point something, you have to now have some form of embedded flow smoothing layer that, regardless of your brand, you have to adapt. I think you, quote, as a public agency, can do a lot of good to your traffic, because first, there's going to be less push, stop, and go traffic, which for IC vehicles is still less emissions. For electric vehicles is at least less expenditure. But there's also an indirect benefit, which is there's a very close correlation between speed variance and stop and go waves and crashes. So even if one day all vehicles are electric, stopping the wave is still good because it will reduce the number of crashes. So I think that one thing where the forum, Jinhua, could be a really good venue if one day we do a fireside chat or a panel, would be, you know, what is the role of public agencies in starting to mandate regulations on autopilots so that it forces some form of mixed autonomy collaboration in between cars that have no individual incentive as companies to do it. And only a public agency can do that because the economics of that is not in favor of collaboration. But regulation can do that with new technology.
That's great. You anticipated my question on this. Indeed, I'd like to organize fire chat to continue this conversation. I'll just add one more point to that. Between the two extremes, one extreme is an individualized car, only consider its self-interest, versus a full social architect, DOT, represent the collective interest. In between, what if we think of this fleet management, like a Waymo? Let's say I have 1,000 cars running around this corridor there, right? Let's say I say 5% of traffic, right? How much a gap between the interest of a Waymo just for the sake of serving this 1,000 Waymo car versus the global optimal? Would that be close enough for the Waymo to have the interest to behave publicly anyway?
I can't comment on Waymo, but Waymo is a typical example of a company that would have such capabilities. You could think of, you mentioned Tesla earlier, which have enough cars to have similar things. And then you could think of Amazon with all the delivery vehicles. One day might have automation, FedEx, USPS, you name it. So I think the canonical example of a fleet is a great example because, and specific fleets like buses or trucks are even better because they are by nature flow smoothers. The dynamics of a truck or the dynamic of a bus is much smoother than the dynamics of an individual vehicle. And I really think that there's a there in the sense that fleets are easier to regulate because essentially you own the fleet, so you can deploy all the algorithms on the fleet yourself. So that's great. It's like a one-stop shop versus essentially a customer base. The second part is that the fleets in general will have, for some of them, better communication. Like you mentioned Waymo. Obviously, the stack of automation there is phenomenal. So while our cars had essentially a cell phone in it, except it's in the car, to communicate, if you have way better communication, then you can do V to I to X or V to I to V much better than through the cell network. So that's better. And then the economics of it is interesting. Ultimately, TNCs like Uber and Lyft at some point were so successful that they were interested in some ways in fixing the traffic problem, because if you have too many TNCs in a location, then you create your own traffic. And if you create your own traffic, you decrease the level of service to your customers. So I think there's a there. I think it's a bit at the frontier of altruistic economics, in the sense that you want to help the system and maybe you get some rebate from public agencies for it. And then, selfish optimality, which is good too, because if you improve local traffic for yourself, you improve it for people. So Maybe a short answer to a long speech is I think that the opportunities with fleets have to be found at places where their operations can support it. And I think it would be fantastic if any of the examples of fleets we mentioned before found interest for a local pilot. And you know, I think it's going to happen within the next couple of years organically. And again, a call to action that if anybody is interested, we're very excited to help and at least have a conversation.
Indeed, nice. Yeah. So for the last 12 minutes, I'll give it to John for the question from the audience. John, please.
Super, Alex. We had a very, very active chat. So just to start out, there was a set of questions around the scalability of this. And first and foremost, I mean, your findings were extremely compelling, great results. How do we actually expand this to other road networks around the country? And so the first set of questions was really about standards. And you did touch on this a little bit in the conversation with Jinhua about regulation. Maybe that is all that is required, a sort of regulatory forcing function. But to start out, so Bern Grush had a question, will we need a standard to ensure that all ADS use the same parameters? Is somebody working on this? And then in the similar vein, Giuseppe Folonari had the question, to the point of architectures becoming closed, from a policymaking point of view, would it make sense to evaluate mandating some degree of openness and interoperability between systems to offer better monitoring and orchestration at the infrastructure level? So that's a kind of family of questions. Your thoughts on sort of standards and scalability of these systems?
Thank you so much, John. Let me start with scalability. People ask us, okay, Alex, so you've done 100 car tests. Are you going to do 1,000 car tests? And the answer is absolutely not, because the model we had, it really doesn't scale. Like taking cars, unplugging it, doing your stuff, replugging it, it's really, that's 100 is as far as we can push it. You want to push it later, maybe phone apps or things like this. But the next stage in scaling has to go through the architecture of the manufacturers. And so, as we mentioned, maybe some companies that have market products out there in the level 2-ish zone can push it, and others maybe who are in the level 5 can probably do that too. So I think the scaling has to happen by some companies embracing it and declaring, okay, we're going to do it. So okay, so that's the path. It's a difficult path. As we mentioned, incentives are needed, but technologically, there's just no other way. I think we've pushed it in the experimental setting as far as we can.
So sorry, just to simplify, so it needs to be industry-led.
Yes, I think so. Yeah, okay. I think I mean, it could be a university-run pilot, but it needs to be an architecture and an implementation that is private sector based, because we've reached our limit as a university. We can't go beyond 100. So that raises the second question you posed, which is the question of standards. Because, well, if just one company is doing it because they want to pioneer it, maybe that's fine, they can do it on their own. But as soon as 2 companies are doing it, then, okay, now there needs to be standards. I am not fully up to speed as to what's happening at the federal level on this front, but the analogy I would take is in air traffic control. Essentially, you have a variety of fleets of aircraft of different manufacturers, and within the same manufacturers, different brands. And so something simple like the air traffic control system has enforced regulations on altitude within high and road sectors. You can fly on even levels or odd levels depending on your directions, set speeds and things like this. I think that first level standard like this in terms of specs, operational specs, is probably a first step. And then I think that would naturally work itself into the lower stacks of the vehicle. Is like, okay, so now if you have speed targets by, say, sector, so a 1 mile freeway has a target speed of 67 miles an hour, blah, blah, blah. How does this map into the architecture? That would then create a maybe more technical conversation of the specs at the manufacturer level so that they would know how that would happen. Which again, I think at the end, we all go back to the public sector. The agencies is like some agency has to convey a group to discuss this, and likely why? Because there is a regulation looming where some lawmaker will try to pass a law to enforce it.
Super. There was a second set of questions around human behavior. So, for example, Saul Tannenbaum asked, is the assumption here that all vehicles are, quote, well behaved, or are the algorithms sufficiently robust that they deal with the adversarial behavior? And in a similar vein, David Ruth asked, how did you control for human behavior of the testers versus typical drivers? We've all been in the situation where we leave a nice safe gap when we're following a vehicle on the highway. And of course, somebody, drives around us and scoots right into that nice safe gap. We've wondered with Kathy's work as well, do we have this risk of people sort of recognizing that these are automated or controlled vehicles and just sort of scooting around them and actually changing their behavioral characteristics?
Yeah, so that's a fascinating domain because first because of natural human behavior, but then because of behavior of human messing up with automation intentionally. Algorithms, I think, hopefully are designed safely enough that they will behave well. So the first natural question is then, okay, how do humans react to automation when they're in different vehicles? And the natural thing that people have observed, I think, since generation 1 automated highway system is that as soon as there is more than 3 seconds gap amongst vehicles, then the temptation is that someone will just take over naturally, not even gaming the system and whatnot. So that's something that we have incorporated into the learning algorithms that we built. In other words, we know that there's lane change models, and we know that these lane change models produce changes which, when there's a certain gap, will essentially lead to people merging in. And therefore, I think that if we incorporate that in the learning, at least we can reach the maximum optimality of what automation can do, given that humans that are not participating will behave a certain way. It's like if you leave, it's like this kind of a saying of when there's a vacuum, nature will fill it. So I think that can be incorporated, and in some ways, I think at several levels of penetration, this kind of human inoptimality added to automation will be dealt with the best it can, given the constraints of the automation. I think the thing which is less obvious is people intentionally messing up with it. So the famous videos you see on YouTube of, oh, I'm going to go in front of the Waymo to see what it does, or oh, I'm just going to mess up on purpose to see this or that. That's another fascinating domain that we've not even scratched. But yeah, I mean, attacks, and then if you push it even more, cyber attacks are things that are another layer that should be dealt with that probably comes later once adoption is a bit higher. But I think the first step is really modeling the human in its interaction with the automation so that you can have the automation operate at the optimality limit beyond which you know that you can push it, because human behavior cannot be countered at a given penetration.
Super. Very early in your talk, Jane Lappin posed a comment and a question. I don't know if you know Jane, but she worked for many years at the Volpe Center at Toyota Research Institute, one of the founders of the Automated Road Transportation Symposium. So, she has a lot of background in this exact area. And her comment was, we have an opportunity to turn AVs into safety agents among the human-driven fleet by discovering the optimal speeds and driving behavior for different traffic roadway conditions and different levels of AV integration into the human-driven fleet. And she goes on to talk about sort of the impact could also include flow stability, reduced fleet emissions, improved throughput, which you alluded to, and of course, improved fleet safety. And her question is basically, have you considered this vein of inquiry in your research?
Yeah, so these are things where first I'm in. This is absolutely fascinating and very important. That's what we're doing now. And the I-24 Motion testbed of Nashville is actually the best source of data for this. So I think it's very interesting because what happens is that we know the natural speed limit of humans on a stretch of freeway is in general different from the posted speed limit. So canonical example in the Bay Area is the I-280, where the casual speed limit is 75. So if you actually go at 65, which is the posted speed limit, you might be a safety hazard because the surrounding traffic is 10 miles average over you. And so first of all, I think that instrumentation will enable now this to be discovered within a decade. Like you could argue Gen 1 GPS in 2008, oh, fantastic, we get speed everywhere. That's how Google Maps, Apple Maps, etc. were born. But now I think the granularity of the data with all the probe vehicles on top of the instrumentation give us really this data almost lane by lane. And if not, as soon as we have enough Teslas and Waymos and of this world on the road, we will have it lane by lane. And so I think that the logical corollary to that is indeed that flow pacifiers like AVs will act, or if they're programmed properly and if the type of algorithms that go on board really take this into account, will act as safety agents. Just because the flow pacification is just the first, step to it. But even if you think about snail operations of the police that they do sometimes when they reopen an asset like a bridge, I mean, these things can be pushed to a fleet and automatically be embedded. And then that brings me back to the previous question, which is, okay, so let's have a framework for this collaboration that is institutionally promoted by an agency or somebody, so that that collaboration is enabled and hopefully in the case of safety can really be designed to support safety improvement goals.
Mm-hmm. On that, Alex, we were discussing the idea of instead of regulating the speed, regulate the deviation from the average speed in the neighborhood, right? This idea never been implementable, but today we may consider the possibility from technology.
And I love that you said that, because this is one of the terms of our loss function in our deep reinforcement learning algorithm. So, so spot on.
Perfect. Yeah. Alex, thank you so much. This is really amazing presentation conversation. Everybody, please join me. Thank Professor Bayer for today's discussion.
Thank you so much. I'm really excited to be here today with you. Thank you, Jinhua and John, for organization and moderation. Thank you, MIT, for this amazing program. And definitely looking forward to seeing you online in the next editions too.